Well, I will start my speeches following this sequence of contents, starting from the main background and the key challenges encountered in the manufacturing of the aerospace composite-titanium stacks to the numerical investigations, the orthogonal cutting experiments in order to identify the fundamental mechanism controlling the chip removal process of the composite stack manufacturing. And then I will introduce the processes for the twist joining, for the hole making, in order to assemble the different parts of the composite stacks for the aerospace applications. And the last two subsections concerns the solutions, the manufacturing solutions to the aerospace composite-titanium stacks, using the vibration-assisted joining and the minimum quantity lubrication joining technique. And finally, some key conclusions and some new inspection implications and the perspectives on how to improve the machinability of the CFRP titanium stacks will be put forward. Well, I start from the first part, the machining challenges to the aerospace grade composite titanium stacks. Well, in the modern aerospace industry, there is an ongoing demand on the advanced materials possessing both the lightweight characteristics and the superior mechanical physical properties. And under this circumstance, the fiber-reinforced polymer laminates has been emerged and has been a promising alternative to conventional steels and mechanical alloys in a variety of industries. And basically, the fiber-reinforced polymers basically consist of two disparate phases. The first one is for the reinforcing fibers, basically exhibiting the higher hardness, higher abrasiveness, and the second phase is for the matrix polymer. The matrix polymer basically plays the role in protecting the fibers. So in general, the fiber-reinforced polymers shows the anisotropic machinability, which is a great challenge to the modern manufacturing community. Additionally, the fiber-reinforced polymers have found their potentials in a variety of industries, such as the wind power, the aerospace industry, automotive, energy, and the electronics. Even though the fiber-reinforced polymers have several advantages in properties, they often been employed in conjunction with the mechanical alloys, such as the titanium alloys, to form a hybrid composite structures to improve the energy savings and the system performance of advanced aircraft. So if we look at the right schematic diagrams for the new generation Boeing 787 aircraft, it is estimated that the hybrid composite stacks has taken about 50% of all the material distributions in the new generation aircraft. Even though the CFRP and the titanium stacks has shown excellent mechanical physical properties and great potentials for their industrial applications, machining of this type of hybrid composites has posed great challenges to the manufacturing sectors. This is due to the disparate natures and behaviors of the mechanical alloy and the composite phase. Additionally, the interface linking both the composite phase and the titanium phase also represents the most weakest long vulnerable to severe joining-induced damages. So in general, or in a word, we can say that the key challenges faced by the current manufacturing sectors include the higher fourth generation, the poor surface quality, as well as the rapid tool wear for the manufacturing of this type of sandwich. It is also reported that the key cause to the failures of the aerospace composite titanium stacks are the defects induced by the joining processes, because we needed the joining operations to create tens of thousands of holes for an aircraft component in order for the final assembly purpose. So there is a critical need to understand the fundamental mechanisms and the machining behavior of this type of biomaterial systems. So in the first part, we have carried out the numerical investigations. We have developed the finite element models using the Abacus explicit code in order to modeling the cutting processes of this type of sandwich. And here we just adopt the orthogonal cutting configurations in order to simplify the complicated geometries of a geobit. So for the constituted models, we basically utilize the three types of constituted models. The one is for the titanium alloys. We just utilize the Johnson-Cook models in order to replicate its machining responses. And for the commodity materials, we just utilize the hashing criteria in order to model the features of the fiber and the metric systems. And finally, is for the interface. The interface just links both the mechanical phase and the commodity phase, and we just model it using the cohesive zones, following the linear, elastic, and softening criteria. And during the numerical simulation, we also carry out several types of experiments to validate the model. So the next slide just presents the results of the cutting processes for the manufacturing of the CFRP titanium stacks. So it is apparent that there are basically three types of machining processes involved. The first is for the manufacturing of the titanium phase, which produce the continuous chip formations. And when the cutting edge is cut into the interface regions, if we look at this schematic diagram, we will see there is a V-shaped like denomination damage. And finally, when the cutting tool cut into the commodity phase, the CFRP phase, it will result in the powdery chip formations due to the brittle fracture dominated chip removal mode. The next page just shows the comparison of different fiber orientations on the machinability and the cutter surface morphology for these CFRP titanium stacks. So if we look at the below two types of images, it is apparent that increasing the fiber orientation will definitively deteriorate the machine surface quality. It will increase the extent of the fiber matrix failures. Additionally, we also carried out some types of the orthogonal cutting experiments. And in this experiment, we have finalized this workpiece, the titanium and the composite using the shape machine tools, and by using the PDD insert to finalize the orthogonal cutting process. And here it just presents the comparisons of the high-speed camera documented images following the chip removal process. So basically, when the cutting tools firstly cut into the CFRP phase, it will result in the powdery dust. However, when the cutting process was operated from the titanium to CFRP, it will result in a severe cracking due to the titanium chip ejection. And additionally, if we increase the fiber orientation to 19 degrees, it will severely degrade the machine commodity surface qualities. So here you will see there are lots of crackings and interlaminar debondings inside of the commodity materials. And moreover, we also carry out the fundamental studies on the conventional twist drilling process for the CFRP titanium stacks. And we carried out this experiment using the titanium aluminum nitrogen coated twist drills. And they utilized the workpiece for the CFRP titaniums are of the identical diameter of 4 millimeter diameter. And here we just compared the different cutting sequence strategy from to the titanium, and then from the titanium to the commodity phase. And then we compare the results of the drilling torque as well as the denomination damage of the commodity phase. So it is clear that machining from the CFRP to titanium basically entails the higher levels of draining thrust force. And by contrast, for the delamination damage, if we machine from the titanium to CFRP, it basically generated a higher level of delamination damage. And this is due to the loss of the support from the bottom titanium in increasing the stiffness of the last fiber pliers. In addition, we also carried out the studies on the three-dimensional topographies in terms of varying the feed rate. So it is clear that increasing the feed rate basically deteriorated the machine surface quality. We will see that the machine surface quality consists a lot of damages, defects, the surface cavities, or the fiber pour out. And the next one just shows the comparisons of the different machining sequence using the SEM images. So we will see that when we perform from the titanium to the CFRP, the machine surface quality are much better than those produced under the sequence from CFRP to titanium. This is because when machining the CFRP first and then to the titanium eventually, the produced titanium chip will evacuate slow the whole wall of the composite face, which will cause severe abrasions and erosions onto the composite surface, resulting in the deteriorations of the CFRP surface. The next part is concerned with the machining solutions. The machining solutions through the aerospace grade composite titanium stacks. So as has been discussed previously, we have been knowing that machining of the CFRP titanium stacks has faced a significant challenge, particularly for the poor titanium chip evacuations. So in order to minimize the detrimental effects arising from the titanium chip ejection, we have to introduce the no vibration, no frequency vibration machining technique. So if we look at this images, okay, it gives you the cutting tools, the experimental setup for the cutting tools, and then we introduce no frequency vibration for the cutting tools. Then the cutting tools will have interrupt contact with the titanium chips and the composite face. So this will allow several times for the heat dissipation, and it will also reduce the contact time during the chip removal process, which can greatly reduce the draining thrust force as well as the machining temperature. So the next page just presents the comparative results between the conventional twist draining and the advanced low frequency vibration assisted draining techniques. So it is apparent that the use of the low frequency vibration assisted draining can greatly reduce the draining thrust force. And additionally, the use of the low vibration can also greatly improve the surface quality in comparison with the conventional twisted machining. The next idea is to introduce the lubrication inside or between the tool chip interface and the tool workpiece interface in order to reduce the frictional coefficient between the chip and the cutting tools. So the below figures just present a schematic diagram for the minimum quantity lubrication systems, and we just spread the minimum quantity lubrication inside the inner holes of the cutting tools, and then the oil will spread directly into the cutting looms, which can reduce the machining temperatures and reduce the frictional force. And here the slide just gives the comparisons of the results of the surface morphologies in terms of the MQL condition and the dry cutting conditions. So it is clear that if we use the use of the minimum quantity lubrication can greatly reduce the extent of the machining-induced damages. By contrast, the conventional dry cutting conditions basically entails the generations of severe damages or a lot of defects. Additionally, if we look at for the factors of the hole geometrical accuracy, okay, for the hole diameters or the hole symmetricity errors, it is also apparent that the use of the minimum quantity lubrication can greatly reduce the air loss for the hole geometries. Okay. Additionally, the use of the low frequency vibration assisted drilling can also improve the tool life. For example, it can reduce the tool wear extent as a comparison with the conventional twist drill. So finally, in conclusion, we can say that machining of the Composite-Titanium stacks has faced the greater challenges of the modern aerospace manufacturing sectors. In order to improve the machinability, the use of the low-frequency vibration-assisted technique and the MQ machining technologies can be applied in order to improve the surface quality as well as the tool life during the chip removal process. And finally, the studies also give us some implications or new perspectives for the future work. For example, the manufacturing sectors have to optimize the tool geometries and the coating materials that match well with the machinability of the CFRP titanium stacks. And secondly, the manufacturing engineers have to develop a more cost-effective strategy for the high quality and high efficiency machining of CFRP titaniums. And finally, it is recommended to seek to apply the advanced manufacturing techniques such as the clean manufacturing, the green manufacturing, or the non-traditional machining processes for the